Hello, everybody. Thanks for tuning in today. I'm Richard Pinnow. I'm Business Development Manager for Computer on Modules. On behalf of ADLINK, I would like to welcome you to this session. Today, we are going to discuss about high-performance computing with Computer on Modules. Basically, looks like this, but we are going to have a look on the details later. ADLINK as a company has been founded in 1995, meaning we are in the embedded business right from the beginning, since computer on modules or the computer on module concept has been introduced to the market first time. The purpose of the today's session is to get you an introduction to the high performance computing stuff based on computer on modules, which are called, or in short, it's called COM-HPCs. And complemented by additionally 3 concrete application examples to explain really practical benefits. Let's start to get you the big picture first. So in most applications, the success rate of brilliant ideas is often depending on how fast you can move from a concept to tangible results. For this, all the tiny puzzle pieces needs to fit well. Computer on modules are unique and have a lot of benefits. So, but first of all, let's have a look on the naming. Sometimes it's confusing, right? So computer on modules and system on modules, maybe you've heard about both terms, are basically the same. So it's a complete embedded computer with a processor on board, chipsets. Sometimes the chipset is embedded in the CPU SoC itself, but sometimes it's not. So then additionally, you have always memory on board or memory interfaces and peripherals to be designed on a single board with a small footprint. And yeah, and this computer on module integrates or is nothing else than a complete functioning computer on a single module. Computer on modules can be based on x86 CPUs, ARM SoCs, FPGAs, for instance, or even GPUs, or hybrid architectures, like, for instance, I expect you heard about this NVIDIA Jetson family, for instance. It blends ARM ingredients with GPU accelerators. Especially COM-HPC is not limited to x86 and ARM implementations. This is very important. The memory interface is one of the most complex layout disciplines, and computer on modules can be seen as an application-ready function block, including a reliable memory interface on module. So system memory is typically embedded in 3 ways. It is soldered down on module. It is based on SODIMM or DIMM type of memories you can insert here, for instance. There are computer on modules out there which are proprietary, so while others are based on industry standards. In this case of an industry standard, system engineers and end users who really wish to have a future proof of their systems, it's the best option to use an industry standard that is supported by many different COM vendors. So this means you have really a dual sourcing approach and you're not locked to one specific vendor. Open industry standards are the best bet and to be well prepared, for instance, against allocation and shortage, which is causing a lot of headache right now. So second source options are lowering the risk for customers and end users. The PICMG and the SJET are the prominent COM standard bodies out there on the market. These are non-profit consortium of companies and organizations that collaboratively develop open standards like COM-HPC, like COM-Express, like SMARC. And these modules are intended to be implemented, for instance, in high-performance telecommunication equipments, in industrial machines, test and measurement equipment, medical and edge devices, for instance, just to give a few examples. ADLINK is a funding member of the SJET and the PICMG with really strong voting rights to really, well, this explains that we are not just following an open standard, we are part of it, we're creating new standards to the market, like COM-HPC, for instance. Computer on modules are always required to be mounted on a carrier board, which breaks the module interface out to standard peripheral connectors. Since computer on modules and system on modules lacks the standard connectors for any input and output peripherals to be attached directly to the board. And this is basically the clue, right? So the carrier board of the client can implement special I/O interfaces, additional memory devices, and connectors according to the application requirements, while the computer on module itself remains a commercial off-the-shelf item. So customers can really concentrate on their mission to contribute their core value proposition without wasting time for complex CPU and SoC implementation. ADLINK offers really a one-of-a-kind computer on module portfolio, which is well balanced to cover all our clients' needs, which are very diverse, right? So what does it mean, a well-balanced computer on module portfolio? So in a nutshell, ADLINK figured out a successful way to be searching for new markets while executing known markets. So executing means we are launching incrementally improved products to serve existing and adjacent markets, which are well known to us. So customers can rely on comprehensive computer on module portfolio, which is cost-effective, proven, and ready to be implemented in a very broad field of applications. Platforms, for instance, like the LCAT Lake, which is the up-to-date Atom, Intel Atom class platform, Tiger Lake UP3, V2000, Tiger Lake H, IMX8M+ from NXP, and Alder Lake P, to name the high-performant platform, are very good examples. They are well-established module form factors are SMARC and COM-Express, while COM-HPC is really a newcomer and covering something new, right? And for this reason, COM-HPC is part of our searching activities. So searching means we are launching new products to target for emerging and new markets. New products and offerings like our COM-HPC server module with equipped with the Ampere Ultra SoC based on ARM technology, Intel Ice Lake D, so really high performance server class x86 performance, and a COM-HPC client based on the Intel Alder Lake P. The exponentially growing edge computing market segment demands ever higher and higher performances and even greater quantities of system memories. So this was basically driving COM-HPC. The embedded processors used in high-end and edge systems can have up to 20 cores or even more, talking about ARM solutions up to 128 cores. And this combination of multiple processing cores and virtualization means that some systems require system memories up to 512 gigabytes of system memory, or even more. Another consideration is that many applications demand extremely high data bandwidth, which may range up to 100 gigabits per second. And COM-HPC, the new COM-HPC specification addresses all these high-end requirements. So ADLINK provides a computer module portfolio which scales from high-end to best cost solutions. Today, we are having a closer look on the red boxes here. So, but to get you the big picture, SMARC with a thermal design power with up to 12 watts is really describing our best cost solutions, so the entry-level products. Complementary Atom class solutions on COM-Express Type 10, for instance, or Type 6 in case the client requires more I/O interfaces. Efficient I-core performance with around 25 to 35 watts on Type 6 compact. And high-performance iCore solutions, which are typically limited to 45 watts on Type 6 basic and 85 watts on Type 7 basic form factor. And this is how COM-HPC comes into play, right? So COM-HPC covers the area that COM-Express at the moment doesn't cover. And COM-HPC itself comes into two flavors. So these are called client type and server type. So COM-HPC client type with up to 90 watts thermal design power of the CPU complements the typical use case of COM-Express Type 6, while COM-HPC server type with up to 200 watts complements COM-Express Type 7. It's a very important statement here. I just want to repeat it again. It's important that COM-HPC is no replacement. COM-HPC is meant to complement COM-Express. So you might be asking yourself, what is the difference between COM-HPC client and COM-HPC server? Let's have a look on the details. So on the left-hand side, you see a comparison table between COM-HPC server, which complements COM-Express Type 7. And on the right-hand side, you see the same comparison table between COM-HPC client and COM-Express Type 6. So what are the major differences? So basically, COM-HPC offers 4 times more PCI Express bandwidth. And having a look on the display interfaces, so server and Type 7 is intended for headless operation, so means typical server applications where no display is involved. And client and Type 7 features up to 4 4K display interfaces. Server applications are really hungry with regards to system memory. For this reason, COM-HPC switched from SODIMM to DIMM memory, which offers twice times higher memory in direct comparison, and which is the best trade-off, by the way, between cost and performance. With regards to Ethernet, it offers 5 times more bandwidth, covering 10G Ethernet for non-headless or typical COM-Express Type 6 use cases. Then something new is USB 4 or Thunderbolt. It is ready to cope with that as well. And at first time offers sophisticated remote management capabilities, but I'm going to mention some details later. And basically, what you've seen here is some CPUs require more PCB space than it is typically available on COM-Express, what you can see here. So basically the COM-HPC server module, so the CPU itself is on the same footprint like the entire COM-Express module, right? So the standard itself defines more PCB space, and it allows higher electrical design power to get from the carrier to the module to really power these demanding CPUs. COM-HPC modules addresses the needs of a very wide range of markets and application areas that require various combinations of high performance and or high memory and or high-speed interfaces, what you can see on the left-hand side. So these include, but is not limited to, for instance, autonomous vehicles, robotics applications, unmanned aerial vehicles, and a 5G communication equipment. For instance, like 5G small cells, base stations, and so on. There are a number of big drivers for COM-HPC, for instance, task consolidation. So consider, to give an example, consider today's trains, for instance, which may involve multiple IT-based service handling tasks as reservation management, onboard Wi-Fi, video surveillance, and so on. All these services are typically provided by different companies in different single boxes, right? And these boxes are scattered throughout the train, right? So, and the consolidation of all these tasks into a single COM-HPC box, and each of these tasks is running on its own virtual machine, for instance, with its own assigned memory. So will dramatically reduce the deployment and maintenance cost and resource for such kind of applications, because it's all processed on one module, right? So it's not distributed anymore. Let's have a look on the next-gen high-performance computer module platforms with its state-of-the-art platform features on the right-hand side. It offers a huge amount of PCI Express Gen 4 lanes up to Gen 5 in the future. Much more memory capacity, higher memory speeds based on DDR5 technology, extreme rugged-ready designs proven against shock and vibration, allowing really reliable extended temperature operation. And yeah, and first time it offers discrete integrated remote management capabilities. So this is getting more and more important, and it supports Ethernet speeds up to 100G. So yeah, let's have a look on some applications. Customers are usually paying for products and services which solve or supports to solve their problems, right? And therefore, let me invite you to have a jointly look on 3 proven COM-HPC success stories. On the next slide, I'm going to have a closer look with you on real applications where all those new features became a crucial customer enabler. So the first application is in-vehicle sensor data collection. The second is extreme rugged edge server for mission-critical applications, and a turnkey solution for the SOFI framework used in automotive and autonomous driving applications. So the first application, so this particular application is called in-vehicle sensor data collection. It's all about high-end data logging to allow efficient validation of automated driver assistance systems, for instance, onboard networks, as well as autonomous driving functions. One of those systems is typically consisting of a data logger, some removable data storages, and copy stations. And yeah, all those gathered data from the sensors are demanding a lot of bandwidth, right? And yeah, further increases in performance are possible through the parallel use of multiple data loggers. So this requires a very good uplink between different modules in case you're designing in multiple modules into one system. So the first differentiator, COM-HPC, offers high performance computing boosted by up to 1 terabyte of system memory capacity. So not surprisingly, when it comes to memory hungry markets, for instance, like COM-HPC is a target, the major consideration for embedded system architecture and developers is then driven by cost of the memory, right? So, and COM-HPC server, in contrast to the more compact COM-HPC client and COM-Express in general, features DIMM memory. And DIMM memory has its best performance per dollar with a sweet spot of 8 times 64 gigabytes, which is very important, especially when resource-hungry hypervisors are part of the customer's software stack. What you can see here is the server type comes into 2 predefined footprints. So the size E, which is capable to host up to 8 DIMMs, which equals to 1 terabyte by using LR DIMMs, and size D footprint, which is a kind of substandard, which can host up to 4 DIMMs, which equals to 512 gigabytes by using LR DIMMs again, at this point. So clients comes and the COM-HPC client comes in 3 footprints. So the size C, size B, and size A footprint. In direct comparison, I put there the COM-Express Basic just to get you a feeling for its size. So size A equals basically to COM-Express Basic, and therefore there's just a very little market overlap given, right? But all the COM-HPC client modules can host up to 4 SODIMMs, which equals to 128 gigabyte memory capacity in total. And this is, in contrast to the server type, it is the best trade-off between performance per dollar and per square centimeter, because it needs to be compact, right, for some applications. Next differentiator, COM-HPC offers more pins and higher transfer rates per pin. So the board-to-board connector has been designed by Sumtech, and it is licensed to other vendors as well to effectively allow a second source approach, right? And one COM-HPC module has 2 times 400 pins, which are running up to 32 giga transfers per second. And yeah, this bandwidth accommodates even the most demanding embedded SoCs, which are currently available on the market, while ensuring enough bandwidth and headroom for the future of the upcoming new CPU targets with way more processing power. So long story short, COM-HPC is well prepared to deal with CPUs and SoCs for the next decade. As I explained earlier, in-vehicle server data collection requires a scalability on a system level. So if the performance on a data logger is not enough, one can simply add a second data logger through its standardized high-speed Ethernet interfaces. So these are ideal to exchange sensor data without the need to design proprietary system uplink interfaces to communicate between 2 modules. You might be wondering, why don't they simply implement commercial off-the-shelf, for instance, 19-inch server solutions, right? It is simple and straightforward to answer. Each vehicle project has its own project-specific high-speed interfaces, which have to be anticipated. So, and a COM solution is the best choice because one can modify the underlying carrier board quickly while keeping the centerpiece, the COM-HPC module, untouched as it is. So this really helps to scale the software ecosystem efficiently and without too many changes. And secondly, one can simply leverage our public available carrier board design resources and which speeds up the implementation, the carrier board implementation of our clients, right? So this is very important. We will make all this information available, but I'm going to share some details 1 or 2 slides later. Let's have a look on the next application. The next application is extreme rugged edge servers for mission-critical applications. So what is important here? ADLINK's COM-HPC solutions provide extended temperature operation, mechanical ruggedness, and high accelerated live testing called hold testing. Means that ADLINK COM-HPC solutions provide high reliability to demanding clients. And you might be wondering again, why don't they simply implement commercial off-the-shelf 19-inch server solutions? So typically, commercial off-the-shelf server equipment offers commercial temperature ranges only, meaning 0 to 60 degree operation in best case. What is wrong by using this equipment at -20 or -40 degrees? It is simply not booting reliably anymore, which is the worst case for equipment which has to work 24/7 without any excuse. And most cases, those booting problems are caused by memory timing issues, and ADLINK offers unique screening services to really make sure that everything is running smoothly from -80 up to 85 degrees. And this is really the key differentiator. Every single module, together with its memory, will be functional tested and screened in a climate chamber at different temperature levels to really make sure that it works. And this is the key differentiator, comparing it to commercial off-the-shelf 19-inch server solutions, for instance. Another feature, what is more and more important to embedded clients, that we offer BIOS fine-tuning services, which allows, for instance, fast booting mechanisms that systems will boot up within 15 seconds. This can be achieved through implementations called like Slim Bootloader. This is a special bootloader implementation. So, and this is simply not available on standard server 19-inch equipment. Just for your reference, traditional server hardware don't really care about boot up times. Even more than 90 seconds is normal, since it is intended to run always and 24/7. But for mission critical applications, 90 seconds are way too long because every single second counts. Yeah, this implementation has to be fast, small, customizable, and secure. And it is optimized for systems with a critical reliance on boot speed. Small footprints means lower flash sizes requirements, reducing the overall BOM costs. And then it allows fully redundant images for resilient solutions. It is designed with modularity in mind, allowing for easy implementation of furthermore changes and differentiating features. And last but not least, it has to be secure. It supports a verified boot and boot mechanisms, and secure firmware updates are a standard, and so on. Build secure boot options when paired with Intel platform protection technology with BootGuard is a key differentiator, just to name one of them. Many of the early COM modules supported a limited form of remote management functionalities. And remote management functionalities are getting more and more important. And yeah, what does it mean, a standardized remote management functionality? So, and it is typical focused on only low-level embedded management functions. It was in the past, and yeah, and this has been changed with COM-HPC. So remote management functionalities really became very important by the standard, and it has been anticipated. So, and yeah, how is the remote management implemented? It's called IPMB. It's meaning Intelligent Platform Management Bus, with its underlying IPMI protocol layer. It is a standardized message-based protocol for out-of-band monitoring and management of remote server platforms. Which hardware blocks are involved? So typical hardware blocks are the MMC. It's a module management controller, which works in conjunction with the BMC through IPMB and I2C UART, which exchanging information and react with the board management controller. The EC is the embedded controller. It manages power sequencing of module, monitors voltages and currents. It monitors and controls fans and watchdogs and so on. And the board management controller, this is the very important new subsystem which is implemented on the customer's carrier board, which performs all those remote management functions, such as power on and power off, reset control. It monitors and can react based on system information, such as board information, sensor data, and so on. What are the benefits, and how does out-of-band management comes into play? One can, for instance, easily update the BIOS, EC, and MMC firmware remotely, and this is really something new. Nobody has to go to the site anymore. Let's have a view back in the past. In the past, a lot of our clients implemented multiple modules on one carrier board. And in the past, this BMC feature has not been available. So, and how did clients overcome this situation? Some of our clients put multiple COM-Express modules on the carrier, and then they were forced to add an additional computing module for just doing the housekeeping stuff, which is now covered by the standardized BMC approach. So this headache is gone. This is the new architecture. So you have one board management controller in the carrier, no matter how many COM-HPC modules you have on your carrier board. So the third application story is about high performance compute based on ARM technology, specifically tailored to foster the SOFI framework, which enables autonomous driving applications effectively. So let's first of all have a chat about the module first, because high performance computing is not typically an ARM application, right? But this is really something new and disruptive to the market. ARM, Ampere, so Ampere is the SoC integrator. So ARM, Ampere, and ADLINK, we joined forces to really create something new and groundbreaking to the market. It's nothing more than the most powerful and energy efficient COM-HPC server platform on the market. So Ampere packaged up to 80 cores at the moment, and in the near future up to 128 cores of the brand new ARM Neoverse N1 architecture into one single SoC. And the SoC is called Ultramax. And this is just the beginning, right? So as I've mentioned, 128 cores will become available soon, but even this is not the end. We expect getting SoCs available to the market with even more cores. ADLINK is really excited and proud to become of this disruptive movement of providing ready-to-use ARM-based COM-HPC products, not just limited to autonomous driving market, but in this particular case, it is the autonomous driving market to be enabled by this solution. Yes, you've heard right. We are talking about ARM-based COM-HPC solutions. Why ARM-based? It's easy to answer for this market because every in-vehicle ECU in a car is based on ARM architecture. So let's first of all have a quick look on typical in-vehicle ECU architectures and its transition from traditional to domain and to finally to zonal architectures. So the traditional architecture is really a diverse architecture, right? Most production cars today have multiple small cell fixed functional ECUs on board. The domain architecture, in contrast, it is consolidating already a few ECUs. So due to the availability of powerful heterogeneous system on chips based on ARM computing, they try to consolidate the workloads into not so many ECUs anymore. And the zonal architecture, this is the future. So I mean, and the zonal architecture means you have just one single high performance compute module or compute system in a car, and this is how COM-HPC comes into play, right? So, and we want to support the market strongly to getting started with this kind of approach, and yeah, this is our solution to foster this market trend. And what is SOFI? SOFI stands for Scalable Open Architecture for Embedded Edge Compute. So SOFI offers a cloud-native architecture enhanced for mixed critical automotive applications. So what does cloud-native development means? So it simply means that you can run, test, and simulate ARM targets without cross-compiling anymore, because both the ARM technology is in the vehicle and in the cloud, and yeah, and this is the key enabler. This is the key enabler to enable vehicle manufacturers to push over-the-air updates over the entire life cycle of a passenger vehicle, and this is generating new revenue streams. So, and Sophie is a very good example that COM-HPC is not just limited to x86 implementations. ARM is a very important technology on high performance computing, on computer on modules. ARM System Ready is another puzzle piece, which is very important. It enables agnostic high-performance compute for every application, no matter if the CPU is based on x86 and ARM. So ARM found out that they have basically everything in place, like technology, processing power, efficiency, but there's one bottleneck compared to x86. ARM is missing a standardized operating systems and bootloaders. And the entire ARM software ecosystem is very fragmented, and the ARM System Ready approach tries to take away this pain. And our solution is ARM System Ready. That means it simply behaves like x86. It's really magic. I really recommend to give it a try. Another argument why we're going to see more and more ARM designs in fields of high performance compute is ARM offers best-in-class energy efficiency, which allows a linear performance over the number of involved embedded cores. Ampere Altra is on the same performance level or even faster than AMD EPYC 7742 implementations, but it's 42% cheaper. This is a very important finding, and what is getting more and more important is the total cost of ownership. So so it saves, due to its efficiency, it saves a lot of energy. Our computer module comes along with a powerful evaluation ecosystem to enable clients to getting started quickly. Our reference carrier, what you can see here, is capable to host up to 2 NVIDIA DGPUs to even more accelerate its number crunching abilities. So this kind of carrier board we explicitly call a reference carrier, right? So to enable you to getting started fast. As I've shown earlier today, yeah, it's really, one can really feel the power, and yeah, COM-HPC really offers enough space to even host the most demanding SoCs out there in the market. To sum it up quickly, because we are running a bit out of time, these are the 3 market-ready COM-HPC products we have at the moment, which are really ready to use function blocks to getting started with high-performance compute now. So high computing power, basically higher memory capacities, higher bandwidth interfaces are the technology drivers. 5 module footprints are defined to meet the needs of the upcoming high-performance CPUs and SoCs. COM-HPC server and client with its sub-feature set are covering both markets, headless server computing and traditional display-powered solutions. And last but not least, all of these state-of-the-art interfaces become easily available through this brand new board-to-board connector, which is ready to cope with 32 gigatransfers per second on in total 2 times 400 pins on each computer on module. Many thanks for joining and listening to this session. We ran a bit out of time. In case you have any question and we have some time left, feel free to shoot me these questions. I'm happy to answer them. And yeah, here we go. So in case there are no questions at the moment, I hope I could get you some good insights today, and please feel free to reach out to me personally or to connect via LinkedIn, for instance. I'm more than happy to support you in case you consider to use computer on modules in the future for your application. And if there is some upcoming question we can discuss afterwards, after the session, I'm happy to answer your questions. Thanks for participating and listening to this session. Thanks.